This work is focused on sequential Bayesian optimization for adaptive informative path planning with multimodal sensing. We've completely open sourced all code that was used in this work, and it is available at the following repository link. Consider an agent equipped with multimodal sensing capabilities. In this context, multimodal refers to the existence of multiple sensors with potentially different levels of accuracy and cost associated with each sensor. In this case, a rover is equipped with a spectrometer and a drill. The spectrometer requires relatively small amounts of energy, but produces less reliable measurements because it's unable to fully observe the subsurface environment. On the other hand, the drill requires very large amounts of energy, but produces almost perfect measurements of the subsurface. In this work, we represent the belief over the world environment as a Gaussian process. A Gaussian process is a distribution over functions that can be used to predict an underlying function given some previously observed noisy measurements. We formulate the problem as a belief Markov decision process with Gaussian process beliefs and solve it using a sequential Bayesian optimization approach with online planning. To solve the belief MDP, we use Monte Carlo tree search with double progressive widening, which accommodates continuous state and action spaces by limiting the number of children at any specific node based on visitation frequency during the tree search. We evaluate our method on two different benchmark problems. The first is the information rock sample problem. We directly compare our method to previous approaches, such as those presented in Chaudhry et al. The top animation shows the mean and variance of the Gaussian process belief using Monte Carlo tree search with double progressive widening as the agent explores the environment. Bad rocks are shown in red, good rocks in green, and beacons in gray. When the agent visits a beacon location and takes a sensing measurement, it receives a noisy measurement of the true state where the noise is proportional to the agent's distance from the rock. We also introduce a new benchmark problem known as the rover exploration problem, which is directly inspired by multiple planetary rover exploration missions. The rover's goal is to collect as many unique samples as it can while respecting its energy constraints. The rover receives a positive reward for drilling a sample that it has not yet seen, and a negative reward for drilling a sample that is already previously collected. This problem highlights the importance of taking sensing actions to decrease the uncertainty in the belief state before deciding to drill. Our approach consistently outperforms previous solutions by more than doubling the average reward received in almost every experiment, while also reducing the root mean squared error in the environment belief by up to 50%. We completely open source our implementation to aid in further development and comparison.